Hello everyone, and welcome to Comprehensive Rocket Science. My name is Rob Roundtree. Comprehensive Rocket Science is a channel dedicated to providing quality educational content on rocket and spacecraft propulsion, so if that's something you're interested in, be sure to like and subscribe for more content in the future. Now, if you're watching this video, I assume you already have an idea about what a launch vehicle is and how it's used, but we'll start with the basics anyway. The purpose of a launch vehicle is to take a payload into space. The launch vehicles tend to be viewed as cool and amazing in their own right. They're really just cargo freighters for space. The reason for a launch vehicle's existence is that a payload needs to be put into space. The main segments of a launch vehicle include the rocket engine, one or more tank sections, and the payload. Now, in all launch vehicles, the vast majority of both the volume and mass is made up of the tanks, generally a fuel tank, seen in red, and an oxidizer tank, seen in blue. The force pushing a rocket up is generated by chemical combustion that occurs inside the rocket engine. The fuel and oxidizer are mixed inside the engine, ignited, and pushed out the nozzle at high velocity. The force of the combustion causes an equal and opposite reaction that pushes the rocket up. We'll be going into much more depth of how rocket engines work in a future video. Now, it's important to note that rockets are required to carry their own oxygen to mix with the fuel on board. If you know anything about combustion, you know it needs three things: spark, fuel, and oxygen. Here on Earth, oxygen is readily available in the air, but as aircraft and spacecraft get higher and higher, oxygen becomes less available, as the atmosphere is less dense. You can see this as I draw a picture of the Earth with the atmosphere above it. Now, notice how the atmosphere is thicker down at the bottom and thins out up at the top. That's just how it works in real life. That being said, the less dense atmosphere is critical to spaceflight, as it's the total lack of an atmosphere in space that enables rockets to escape aerodynamic drag and actually attain orbital velocities. So spacecraft must carry both fuel and oxidizer on board, because there's no air in space. A common fuel is RP1, another is liquid hydrogen, and another is liquid methane. The most common form of oxidizer is just liquid oxygen, or LOX. We'll go into the pros and cons of different types of rocket fuel in great detail in future lectures. So, now we should have a good idea of how rockets reach space. Burning fuel and oxidizer and shooting the exhaust out the back at high velocity produces a force causing the rocket to go up. As the rocket goes up, the air gets less and less dense. As the atmosphere becomes less dense, the rocket has to fight less against air resistance, or in slightly more technical terms, experiences less drag. This phenomenon, combined with the fact that the mass of the rocket is constantly getting lower as it burns fuel and oxidizer, causes its rate of acceleration to increase as the flight progresses, and allows the rockets to reach ridiculous velocity. We'll go into the rocket equation in depth in future videos, but for now, just think. You have a constant force, a mass that's decreasing. What happens to the acceleration? It's going up. This is oversimplified, but gives you an idea of the basics. And it's important to note that this effect is extremely profound. In all orbital launch vehicles, fuel is the vast majority of the vehicle's entire mass. And you can see here you have acceleration going up with time, velocity going up exponentially with time. Okay, so you have a rocket that's going really fast and gets out of the atmosphere. How does it stay in space? Does it escape Earth's gravity at some point? No, not at all. In fact, all objects in space are constantly under the effect of Earth's gravity, no matter how far away they are, though the effect does get smaller and smaller with distance. This is due to Newton's law of universal gravitation, depicted, which states that the gravitational force pulling two objects together is equal to a gravitational constant times the first mass times the second mass divided by the distance between them squared. Here, m1 is the rocket and m2 is the Earth. Now, even though this force decreases with the distance between the two objects squared, the distance for most man-made objects doesn't even come close to making Earth's gravity negligible. We know that F equals ma, and for free fall, F equals negative mg, where g is gravity. You may think that g is a constant, but this isn't actually true. G is only equal to 9.8 meters per second squared at sea level on Earth, and is actually slightly less than that higher in space. To find g, we can say that F over m equals g, where m is the mass of your rocket. We can use that knowledge to return to the universal gravitation and find g at our distance above Earth, say 200 kilometers, which is about where the International Space Station is. For reference, space is arbitrarily defined as 100 kilometers, so 200 kilometers is well into space. Now, it's important to note that r is defined as the distance between the center of each mass, so to our altitude we will have to add the radius of the Earth to find g. The mean radius of Earth is 6,371 kilometers. So you've got the center of each mass here, you've got your altitude, 200 kilometers. You can say that g, your local gravity, is equal to the gravitational constant times the mass of the Earth plus the radius of the Earth, mass of the Earth divided by the radius of the Earth plus your altitude. You'll see I made an error here, and in the denominator, our Earth plus h1 should be quantity squared. When you calculate this, you end up that gravity, g, at 200 kilometers in space is about equal to 9.23 meters per second squared. Not much different than our g at sea level of 9.81 meters per second squared. So, how does the International Space Station overcome Earth's gravity to stay in space for long periods without firing its engines? The answer to that is that it's in orbit. Basically, it's going so fast sideways that as it falls, the Earth is constantly curving away beneath it, and as a result, it never hits Earth. In this way, it ends up in a circular path where it's constantly falling around the Earth. We'll cover the basics of orbit, then dive into launch vehicle staging and ascent profiles in the next video. So if you're interested in spaceflight and want more technical content, be sure to like and subscribe. Things are going to get more and more technical as we go on, and I'll be trying to give you all the gory details of spaceflight. So if that's something you're interested in, stay posted. Thanks for joining, and I'll see you next time.